So we know that the heat equation is the gradient flow of the entropy with respect to the Wasserstein metric, okay? And one can kind of view the heat equation as almost destroying information about a system. So basically sending the system into a state where there are a ton more of available microstates, and so it's much harder to characterize, or the determinacy of the system is being lost. Whereas the wave equation actually preserves information. Okay, so the heat equation actually forces initial data to become smooth, right? When you apply the heat equation, you're essentially convoluting against a Green's kernel, which is a time-evolving Gaussian from a delta mass, and that time-evolving Gaussian from the delta mass solves the heat equation itself. But when you convolute against that Green's kernel, you get an arbitrary solution of the heat equation if you just convolute the initial data with that time-evolving Green's kernel. So that tells you is that exactly how information is locally getting destroyed in your system is actually via the heat equation is actually maximized, right? The entropy, so the informational content, the expected value of the informational content of each microstate, right, is getting maximized as you apply the heat equation, which essentially means that your system is going into a configuration which has many more possible sub-configurations. Okay, so you know less information about that system. Whereas the wave equation actually preserves information, right? So the wave equation does not regularize its solutions. If you apply the wave equation, you're essentially going to create this this motion of the initial data, right? But that motion, this wave-like motion of the initial data, isn't actually going to destroy information, okay? And so you also have a finite speed of propagation. Now, there's something called fractional calculus, okay? Fractional calculus actually allows you to interpolate between the heat equation and the wave equation, which is really interesting. I have a buddy that was talking to me because his research is on fractional calculus, so he was kind of mentioning his research to me, and it was super interesting. And basically the idea is that in fractional calculus, you can interpolate between the heat equation and the wave equation, essentially using a fractional version of the derivative. You can take a fractional version of the derivative, which gives you an integral equation instead of a differential equation, an integral equation, which essentially can be used to interpolate between the heat and the wave equation. And this interpolation process actually is an interpolation with respect to information loss. So as you interpolate between the heat equation and the wave equation, you're essentially resolving the amount of information lost from like the maximum information loss, which is the heat equation, into no information loss, which is the wave equation, and you're kind of tuning the dial, the entropic dial of like how much entropy, or how much the system is increasing in entropy, right? How much diffusion is occurring, whereas how much of the process is just wave-like motion, propagation of waves throughout space. So this is an awesome this is an awesome like bridge, or an awesome connection between optimal transport theory, the entropy functional, and then the wave equation, interpolating between the heat equation and the wave equation. What does that look like in terms of the entropy functional, and can we use the theory of optimal transport and this kind of geometric structure on the probability space to understand this interpolation better? The interpolation, of course, provided by fractional calculus between the heat and the wave equations.